In 2022, the Space Force publicly announced plans to dramatically expand America's satellite constellations, adding over 100 new intelligence satellites to create near global revisit capability. What seemed like routine military modernization has produced effects that extend far beyond anything previously possible. International negotiations now seem to anticipate moves before they're made. Economic sanctions target specific individuals with surgical precision. Military operations unfold with impossible coordination across continents. The satellites watching us today represent a shift from periodic imaging to constant observation, transforming surveillance from reactive intelligence gathering into something approaching real-time omniscience. But the full scope of what changed in those classified briefings remains hidden behind layers of secrecy. The classified breakthrough that changed everything. What intelligence officials will acknowledge is that a fundamental capability barrier was crossed in 2022, one that transformed surveillance from observation into something approaching real-time omniscience. The breakthrough involved the transition from the film, return Corona satellites that dominated Cold War reconnaissance until 1972 to modern digital electro-optical and signals intelligence platforms that could process imagery instantaneously. Traditional satellite intelligence gathered information about what had happened or what was currently happening. This advancement created systems that could analyze patterns and accelerate intelligence cycles from hours to minutes. The visible effects started appearing in early 2023 when American diplomatic initiatives began demonstrating an almost supernatural understanding of foreign government intentions. Trade negotiations with European partners proceeded with precision that suggested American negotiators knew exactly which concessions their counterparts were prepared to make before those concessions were even discussed internally. Military advisors in conflict zones began receiving intelligence that allowed them to position resources days before enemy movements that hadn't yet been planned. The timing was too consistent to be coincidence and too accurate to be traditional intelligence gathering. Intelligence agencies had spent decades perfecting the art of collecting information after events occurred or as they unfolded. Human assets reported on conversations they had witnessed. Signal intercepts captured communications that had already been transmitted. Satellite imagery documented activities that had already taken place. The 2022 breakthrough changed this fundamental equation by creating systems that could identify behavioral patterns and process them with unprecedented speed. The National Geospatial-Intelligence Agency's Maven tool exemplifies this transformation with targeting workflow timelines dropping from hours to minutes during recent exercises. The number of analysts and operators using these targeting tools has quadrupled since March 2024. The technical architecture behind this advancement involves artificial intelligence systems working in conjunction with neural networks that have been trained on decades of human behavioral data. These systems can identify patterns in everything from travel schedules to communication frequencies to purchasing habits that serve as predictors for major political and military decisions. The processing power required to analyze these patterns across global populations simultaneously exceeded anything previously deployed in space. Each satellite now carries computing capabilities that surpass most ground-based supercomputers from just 5 years ago. Evidence of accelerated intelligence capabilities emerged most clearly in economic sanctions enforcement. Treasury Department officials began targeting specific individuals and entities with sanctions packages that seemed to anticipate financial movements before those movements occurred. Cryptocurrency transfers were intercepted at precisely the moment they were initiated. Shell companies were identified and sanctioned before they had completed their first transactions. The accuracy suggested that American intelligence was not just monitoring financial activity, but processing it with machine learning algorithms that could identify suspicious patterns in real time. Traditional espionage relied on human sources who could report on conversations and documents they had access to. The breakthrough made human intelligence gathering less critical because the AI-driven systems could process vast amounts of data and identify patterns that human analysts would miss or take weeks to recognize. This shift from reactive to predictive intelligence gathering fundamentally altered the intelligence community's operational priorities. Resources that had been devoted to recruiting human assets and developing signal intercepts were redirected toward refining the behavioral analysis algorithms that had proven far more reliable than traditional methods. Foreign intelligence services began noticing that their operational security measures were failing in ways that suggested American intelligence was operating with capabilities they couldn't understand. Russian intelligence officers found that Americans seemed to know about operations that existed only in planning stages. Chinese military exercises were anticipated and countered before they had been fully authorized. The response was a complete overhaul of operational security protocols that assumed American intelligence could process activities based on behavioral patterns rather than intercepted communications or human reporting. The economic implications of accelerated intelligence extend far beyond national security. Satellite systems that can track individual financial transactions from space by monitoring the behavioral patterns that precede those transactions give American policymakers unprecedented insight into global economic activity. Market movements can be anticipated based on the behavioral indicators of key decision makers at major financial institutions. Resource allocation decisions by foreign governments can be processed by analyzing the movement patterns and communication frequencies of relevant officials. This economic intelligence influences everything from trade policy to sanctions enforcement to investment decisions by American companies operating internationally. The advancement rendered traditional espionage methods less efficient almost immediately. Dead drops and secret meetings became less important when satellite systems could process what information would be exchanged based on the behavioral patterns of the participants. Code breaking became less critical when systems could analyze what messages would be sent before they were encrypted. Human intelligence networks that had taken decades to develop found themselves providing information that American systems had already processed through behavioral analysis. International intelligence cooperation agreements had to be completely rewritten to account for American capabilities that partner nations couldn't match or even fully understand. The traditional model of intelligence sharing assumed that different nations brought different capabilities to cooperative efforts. American processing capabilities were so far beyond what other nations could contribute that traditional partnerships became essentially one-sided relationships where America provided intelligence while partners contributed little of comparable value. What emerged from this technological leap was surveillance that transcended traditional boundaries between observation and analysis. The satellites watching from orbit could process human behavior with accuracy that approached real-time understanding. Decision makers found their patterns analyzed before they had recognized them themselves. Organizations discovered their activities processed before they had completed them. The threshold crossed in 2022 created the first truly comprehensive surveillance system in human history, one that could see not just what was happening, but process it instantly. Intelligence had evolved from reactive observation into predictive analysis, and the implications of that evolution were reshaping global power dynamics in ways that most of the world was only beginning to understand. The scale of surveillance capability this breakthrough enabled would require an infrastructure unlike anything previously imagined. The new Constellation Architecture of 2025. By 2025, America operates a satellite constellation that dwarfs anything from the Cold War era. The Space Force reported 83 satellites in service at the end of fiscal year 2023, with plans to launch over 100 additional satellites in 2025 alone, nearly doubling the previously known number of Space Force spacecraft. This represents a dramatic acceleration from the Cold War peak, when a successful year might see 15 new reconnaissance satellites reach operational status. The current architecture operates on 3 distinct orbital tiers that work together as an integrated surveillance network. Low Earth orbit swarms circle the planet at altitudes between 200 and 1,000 kilometers, providing the highest resolution imaging and the shortest revisit times for critical targets. These satellites pass over any given location multiple times per day, capturing detailed imagery that can resolve objects as small as 10 centimeters across. Medium Earth orbit specialists operate at altitudes between 2,000 and 35,000 kilometers, focusing on signals intelligence and communications monitoring with broader coverage areas that complement the narrow focus of the low-orbit systems. Geostationary command centers positioned 35,786 kilometers above the equator maintain constant watch over specific regions while coordinating the activities of the lower orbit satellites. The distributed nature of this three-tier system creates unprecedented resilience against attempts to disable or disrupt American surveillance capabilities. Previous generations of spy satellites relied on a small number of highly capable but vulnerable platforms that represented single points of failure. The loss of one corona or keyhole satellite could eliminate surveillance coverage over entire regions for months until replacement systems could be launched and positioned. The current constellation spreads intelligence gathering across hundreds of platforms, meaning that losing any individual satellite or even multiple satellites would have minimal impact on overall surveillance capabilities. The Space Development Agency's proliferated warfighter constellation exemplifies this new approach, deploying dozens of smaller satellites instead of relying on a few expensive platforms. This proliferated architecture makes the system nearly impossible to disable through kinetic, cyber, or electronic attacks. The Defense Support Program satellites and next-generation overhead, persistent infrared systems provide missile warning capabilities across multiple orbital planes, ensuring that no single attack could blind America's early warning systems. Commercial partnerships have significantly expanded America's effective surveillance capacity through arrangements that blur the lines between military and civilian space assets. The Blackjack program demonstrates how commercial satellite buses can be adapted for military intelligence missions, reducing costs while increasing deployment speed. Companies like Planet Labs operate hundreds of small satellites that provide daily global imagery, with intelligence agencies accessing this data through classified sharing agreements. Maxor Technologies operates high-resolution imaging satellites that serve both commercial customers and government intelligence requirements, creating dual-use systems that expand surveillance coverage without requiring additional government satellite launches. The cost-efficiency breakthrough that enabled this massive expansion came from standardizing satellite components and manufacturing processes. Previous spy satellites were custom-built systems that required years to design and hundreds of millions of dollars to construct. Modern satellites use standardized platforms and components that can be manufactured quickly and at much lower cost. The same basic satellite bus can be configured for different intelligence missions by swapping out sensors and communication equipment, reducing development time from years to months and cutting costs from hundreds of millions to tens of millions per satellite. This architecture provides comprehensive coverage of any point on Earth through multiple overlapping satellite fields of view. The constellation includes enough satellites in the proper orbital configurations to ensure that multiple different satellites can observe any location on the planet throughout each day. This overlapping coverage eliminates the gaps in surveillance that existed when fewer satellites were available and targets could only be observed during specific orbital passes. Multiple satellite views of the same location also enable stereoscopic imaging that creates detailed three-dimensional maps of terrain and structures. The constant surveillance capability extends beyond simple imaging to include persistent monitoring of communication signals, electromagnetic emissions, and thermal signatures. Satellites equipped with advanced sensor packages can detect and analyze radio communications, radar emissions, and electronic warfare signals continuously rather than during brief orbital passes. This persistent monitoring creates a comprehensive picture of electronic activity across the globe that updates in real time as conditions change. Intelligence analysts now have access to surveillance data that covers every square kilometer of the Earth's surface, with revisit times measured in hours rather than days or weeks. This coverage density enables intelligence agencies to track changes and developments as they occur rather than discovering them days or weeks after the fact. The combination of high resolution, frequent revisits, and multiple viewing angles creates surveillance capabilities that approach the theoretical limit of what is possible with orbital platforms. The Constellation represents America's most ambitious surveillance achievement, a system that can observe activities anywhere on Earth with unprecedented frequency and detail. This level of comprehensive coverage transforms intelligence gathering from a selective process focused on specific targets into a monitoring system that captures everything within its field of view. The technical capabilities that make this possible raise fundamental questions about what these systems can actually detect and identify from their orbital vantage points. Resolution. Revolution, what these eyes can actually see. Modern satellites capture imagery with resolution measured in centimeters rather than meters, and the detail they provide has transformed how intelligence agencies understand ground-level activities. The progression from the Corona program's grainy photographs to today's real-time surveillance represents one of the most dramatic technological leaps in intelligence history. Public estimates suggest current electro-optical systems achieve ground sample distances of approximately 30 centimeters, though classified capabilities likely exceed these figures. Corona satellites from the 1960s used film canisters that had to be physically recovered from orbit to develop images with resolution measured in meters. Analysts worked with photographs that could identify large buildings and major installations but provided little detail about specific activities or equipment. The entire intelligence cycle from image capture to analysis took weeks or months, limiting the operational value of satellite reconnaissance to strategic rather than tactical applications. Today's systems provide real-time imagery with 10-centimeter resolution that updates continuously as satellites pass overhead, creating intelligence products that support immediate operational decisions. The breakthrough in adaptive optics eliminated atmospheric distortion as the primary limitation on satellite image quality. Previous generations of spy satellites struggled with the blurring effects of atmospheric turbulence that degraded image clarity and limited the useful resolution of optical systems. Modern systems use sophisticated mirror adjustments that compensate for atmospheric distortion hundreds of times per second, producing images that approach the theoretical limits of optical resolution. These advances build upon decades of sensor development, with the Defense Support Program operating missile warning satellites since 1970 and the Space-Based Infrared System providing enhanced capabilities since 2001. Synthetic aperture radar systems now provide detailed imaging capabilities through clouds, weather conditions, and complete darkness. These active radar systems emit their own signals and analyze the reflected energy to create high-resolution images that penetrate cloud cover and operate in any lighting conditions. SAR technology creates imagery that reveals surface textures, structural details, and even subsurface features that optical systems cannot detect. The radar signatures captured by these systems provide intelligence about material composition, construction techniques, and structural modifications that complement optical imagery with technical details invisible to traditional cameras. Multispectral imaging capabilities enable satellites to detect everything from underground bunkers to individual crop varieties by analyzing how different materials reflect specific wavelengths of light. These sensors capture imagery across multiple bands of the electromagnetic spectrum simultaneously, creating data that reveals information about material composition, chemical properties, and physical characteristics invisible to standard photography. Underground facilities can be detected through their thermal signatures or through subtle changes in surface vegetation caused by construction activities. Agricultural monitoring can identify specific crop types, growth stages, and health conditions that provide intelligence about food production and economic activity. Hyperspectral imaging systems identify materials and substances from their unique spectral signatures by analyzing hundreds of narrow wavelength bands across the electromagnetic spectrum. These sensors can distinguish between different types of metals, concrete compositions, paint formulations, and chemical compounds based on how each material reflects specific wavelengths of light. The spectral signatures captured by hyperspectral systems create detailed inventories of materials present at any location, enabling intelligence analysts to identify military equipment, construction materials, and industrial processes with precision that approaches laboratory quality analysis. Thermal imaging advances now track individual vehicles and people through their heat signatures with resolution that can distinguish between different types of engines, detect recent vehicle operation, and monitor human activity patterns through thermal emissions. Advanced thermal sensors capture minute temperature differences that reveal information about mechanical systems, electrical equipment, and human presence that remains invisible to optical sensors. These thermal signatures persist for hours after activities have ended, creating intelligence about past events and providing predictive information about future activities based on thermal patterns. The integration of multiple imaging types creates comprehensive three-dimensional models of any location by combining optical imagery, radar data, thermal information, and spectral analysis into unified intelligence. Products. These multi-sensor fusion techniques produce detailed representations that show not just what objects look like, but what they are made of, how they function, and how they have changed over time. The three-dimensional models created from multiple satellite observations provide intelligence analysts with virtual reality representations of target areas that support detailed mission planning and threat assessment. Advanced sensor fusion techniques now enable satellite to reveal information about interior spaces and concealed activities by combining multiple types of sensor data. Ground-penetrating radar systems can detect subsurface structures and underground facilities. Thermal imaging can identify heat sources inside buildings and track the movement of people through thermal signatures that penetrate building materials. Electromagnetic sensors can monitor electronic equipment operating inside structures. The combination of these sensor capabilities creates intelligence about activities inside buildings and underground facilities that approaches the detail available from direct observation. The resolution capabilities of modern satellites extend beyond simple visual clarity to include temporal resolution that captures changes measured in minutes rather than days or weeks. Satellites now provide intelligence about dynamic situations as they develop, tracking vehicle movements, personnel activities, and operational changes in near real time. This temporal resolution transforms satellite intelligence from historical documentation into current operational intelligence that supports immediate decision-making and tactical operations. Modern satellite sensors operate across electromagnetic spectrum ranges that extend from radio frequencies through visible light into gamma radiation, creating comprehensive sensing capabilities that capture information invisible to human observation. These multi-spectrum systems provide intelligence about electronic emissions, chemical processes, nuclear activities, and material compositions that traditional photography could never detect. The comprehensive sensor suites deployed on current satellites create surveillance capabilities that can detect and analyze almost any human activity from space, but the raw data they collect requires processing power that transforms these orbital platforms into the AI brain behind the eyes. Each satellite now functions as an autonomous intelligence analyst, processing data and generating actionable intelligence without waiting for instructions from Earth. Modern satellites carry computational systems that enable real-time analysis of the massive data streams they collect, transforming orbital platforms from simple collection devices into sophisticated analytical systems. The National Geospatial Intelligence Agency's Maven AI tool exemplifies this transformation, reducing targeting workflow timelines from hours to minutes during operational exercises. This system now supports over 20,000 active users across 35 different analytical tools, demonstrating the scale at which artificial intelligence has been integrated into satellite-based intelligence operations. Machine learning algorithms aboard these satellites identify patterns and anomalies in real time without human intervention, processing millions of data points simultaneously as satellites collect information across multiple sensor systems. These algorithms have been trained on decades of historical intelligence data to recognize normal patterns of activity and flag deviations that indicate potential intelligence value. The pattern recognition capabilities operate continuously, analyzing everything from vehicle movement patterns to communication signal anomalies to changes in infrastructure development. When these systems detect patterns that match known threat indicators, they automatically flag the information for priority analysis and can trigger immediate alerts to intelligence analysts on the ground. The predictive capabilities embedded in satellite AI systems can forecast human behavior and military movements by analyzing subtle changes in routine activities that precede major decisions or operations. These systems identify behavioral indicators that human analysts typically miss because they occur across timescales and geographic areas too large for traditional analysis methods. Military exercises that appear routine may contain subtle timing or positioning changes that AI systems recognize as preparation for actual operations. Economic activities that seem normal may show patterns that predict policy changes or resource allocation decisions weeks before those decisions are announced publicly. Natural language processing capabilities allow satellites to monitor, analyze global communications by intercepting and processing electronic signals, radio communications, and data transmissions in real time. These systems can process communications in hundreds of languages simultaneously, identifying keywords, phrases, and conversation patterns that indicate intelligence value. The natural language processing algorithms understand context and can distinguish between routine communications and conversations that contain operationally significant information. Communications analysis happens automatically as satellites intercept signals, with AI systems generating summaries and alerts about significant conversations without human analysts needing to review every intercepted communication. Automated threat assessment systems trigger alerts within seconds of detecting suspicious activity by comparing observed activities against databases of known threat patterns and behaviors. These systems monitor multiple information streams simultaneously, combining imagery analysis with communications intercepts and behavioral pattern recognition to identify potential threats as they develop. When multiple indicators suggest developing threat activity, the automated systems generate immediate alerts that reach intelligence analysts and military commanders within minutes of the initial detection. The speed of automated threat assessment eliminates the delays that previously allowed threats to develop while human analysts processed information through traditional channels. Deep learning networks recognize individual faces, vehicles, and equipment across vast geographic areas by analyzing high-resolution imagery and comparing observed objects against comprehensive databases of known entities. These recognition systems can identify specific individuals even when facial features are partially obscured or when images are captured under challenging lighting conditions. Vehicle recognition capabilities extend beyond simple identification to include analysis of modification patterns, usage behaviors, and association networks that provide intelligence about organizational structures and operational patterns. Equipment recognition systems can identify weapons, communications gear, and specialized machinery that indicate specific capabilities or intentions. Behavioral analysis algorithms detect unusual patterns and daily routines and activities by establishing baseline activity levels for geographic areas and identifying deviations that suggest operational significance. These algorithms monitor everything from traffic patterns to communication frequencies to energy consumption levels, creating comprehensive pictures of normal activity that serve as baselines for anomaly detection. When activities deviate from established patterns in ways that match historical indicators of military or political significance, the behavioral analysis systems flag these changes for immediate attention. The algorithms can detect preparation activities for major operations days or weeks before those operations begin by recognizing subtle changes in routine behaviors. Real-time processing capabilities eliminate the traditional delays between information collection and intelligence production that previously limited the operational value of satellite intelligence. Modern satellite AI systems generate finished intelligence products while orbiting overhead, delivering actionable information to military commanders and policymakers within minutes of collection rather than hours or days later. This real-time production capability transforms satellite intelligence from strategic analysis tools into tactical support systems that directly influence operational decisions and immediate responses to developing situations. These AI-powered surveillance systems now operate with sophisticated analytical capabilities that complement human intelligence work, making decisions about data prioritization and generating preliminary intelligence products, while human analysts focus on strategic interpretation and policy recommendations. The integration of artificial intelligence into satellite operations has created orbital intelligence systems that can process vast amounts of information independently, fundamentally changing how intelligence agencies approach satellite surveillance operations. Yet this technological revolution in government satellites represents only part of a larger transformation that extends far beyond official military and intelligence programs. The commercial camouflage network. Companies like Planet Labs and Maxar Technologies operate under public-private partnerships that have been formally declassified through the National Reconnaissance Office's Enhanced Commercial Operations License Program. These partnerships allow intelligence agencies to leverage commercial satellite capabilities while maintaining the appearance of separate business and government operations. Planet Labs operates over 200 small satellites that capture daily imagery of the entire planet's landmass, marketing this capability to agricultural customers, urban planners, and environmental researchers. Intelligence agencies access the same imagery through documented contracts that provide government analysts with daily global coverage supplementing their dedicated military satellites. Maxar Technologies operates high-resolution imaging satellites serving both commercial customers and government agencies through contracts that generate significant revenue while expanding America's surveillance capabilities. The company's satellites capture images with resolution sufficient for detailed intelligence analysis, with government agencies receiving priority access through established procurement agreements. Black Sky operates a constellation of small satellites providing both commercial Earth observation services and government intelligence support through similar dual-use arrangements that have become standard practice in the commercial space industry. The National Reconnaissance Office's Enhanced Commercial Operations License Program formally acknowledges these partnerships, allowing commercial satellite companies to provide imagery and data services to intelligence agencies through transparent procurement processes. These arrangements operate under existing export control regulations and licensing requirements managed by the Commercial Space Coordination Office as documented in recent Government Accountability Office reports. The partnerships provide intelligence agencies with additional surveillance capacity while offering commercial companies stable revenue streams that support their business operations and satellite constellation expansion. Financial incentives encourage private companies to build satellite systems serving both commercial and intelligence requirements through procurement contracts that guarantee revenue streams for companies designing intelligence-compatible systems. The government provides development funding, launch contracts, and long-term data purchase agreements that make dual-use satellite programs financially attractive. These arrangements create business models where commercial satellite companies consider government requirements when designing their systems and operating their constellations, with companies building satellites useful to intelligence agencies receiving preferential treatment in government contracting processes. Commercial satellite imagery is subject to existing export controls and licensing requirements that govern how this information can be collected, processed, and distributed. The Commercial Space Coordination Office manages these licensing processes to ensure that commercial satellite operations comply with national security requirements while serving legitimate commercial customers. Companies operating Earth observation satellites must demonstrate that their systems will not interfere with government satellite operations and must agree to provide government agencies with access to their data when requested through established procurement channels. Data sharing agreements between commercial satellite companies and intelligence agencies operate through standard government contracting processes that specify how commercial data will be accessed and used for government purposes. These agreements require companies to provide intelligence agencies with access to their data streams, processing capabilities, and analytical products through arrangements that follow established procurement regulations. The agreements often include requirements that companies modify their systems to better serve intelligence requirements, effectively creating dual-use intelligence platforms that maintain their commercial operations while supporting government surveillance needs. Commercial satellite constellations provide redundancy for intelligence operations by creating multiple sources of information about the same targets through systems that operate under commercial licenses while serving government customers. Intelligence agencies can access information from multiple commercial sources rather than relying solely on classified military satellites, providing operational flexibility and reducing dependence on dedicated government systems. The redundancy provided by commercial systems ensures that intelligence collection continues even if military satellites experience technical problems or operational limitations. Regulatory oversight ensures that commercial satellite companies serve national security interests through licensing processes that coordinate commercial operations with government requirements. The Federal Communications Commission and other regulatory agencies work with intelligence agencies to ensure that commercial satellite licenses include provisions supporting national security interests. Companies seeking to operate satellite systems must demonstrate compatibility with government satellite operations and agree to provide government agencies with data access when requested through proper channels. Foreign commercial satellites operating in areas of American strategic interest are monitored through established intelligence collection methods that track the capabilities and activities of international satellite operators. American intelligence agencies assess foreign commercial satellite companies to understand their capabilities and identify potential intelligence collection opportunities. Commercial satellites from countries like China and Russia are evaluated as potential sources of intelligence information while also being assessed for their impact on American satellite operations and data collection activities. The hybrid model created by commercial intelligence partnerships operates through established procurement and regulatory frameworks that govern how commercial space companies interact with government customers. These partnerships combine commercial innovation with government requirements, creating satellite systems that serve both commercial markets and national security needs. The commercial space industry provides additional surveillance capacity that supplements government satellite systems while operating under regulatory oversight that ensures compatibility with national security objectives. This dual-use satellite network has created surveillance capabilities that exceed what purely commercial or purely government systems could achieve independently, establishing intelligence agencies as major customers of the commercial space revolution while maintaining distinct commercial and government operations serving different markets and requirements. The comprehensive surveillance network created by these partnerships extends beyond simple imagery collection into sophisticated electronic monitoring capabilities that operate continuously across the electromagnetic spectrum. Signals intelligence, intercepting the digital world. These systems monitor communications across multiple frequency bands through specialized satellites positioned in geostationary and low Earth orbits that intercept specific types of electronic transmissions. The Defense Support Program satellites operating at 22,000 miles altitude provide infrared missile launch detection capabilities, while the Naval Ocean Surveillance System tracks ship emissions from approximately 1,000 miles above Earth. These platforms represent the backbone of America's space-based signals intelligence network, capturing electronic communications that travel through space between ground stations and satellites. Orbital positions provide satellites with strategic advantages for monitoring satellite communications and certain radio transmissions because signals traveling between ground-based systems and satellites must pass through space where properly positioned intelligence platforms can intercept them. The Orion and Orion advanced series satellites operate in geostationary orbit specifically for electronic intelligence collection, positioning massive antenna arrays to capture communications from specific geographic regions. These geostationary platforms maintain constant coverage over target areas, intercepting uplink and downlink transmissions from commercial and military satellite communication systems operating below them. The antenna systems deployed on signals intelligence satellites represent sophisticated engineering achievements designed to capture weak electronic signals from orbital distances. These collection systems focus on intercepting satellite communications, microwave transmissions, and radio signals that propagate through space rather than terrestrial networks. The specialized design of these antenna arrays enables satellites to distinguish between different types of electronic emissions and isolate specific communication channels from the background electromagnetic noise present in space. Signal processing capabilities aboard these satellites analyze intercepted communications in real time for advanced computational systems designed for electronic intelligence analysis. These processing systems can simultaneously monitor multiple communication channels while identifying signals of intelligence value from routine transmissions. The onboard processing power enables satellites to perform initial analysis of intercepted signals, filtering communications based on frequency patterns, signal characteristics, and transmission protocols before transmitting selected intelligence back to ground stations for detailed analysis. Electronic signature analysis enables satellites to detect and identify different types of electronic equipment based on the unique electromagnetic emissions that various devices produce during operation. Every electronic system generates distinctive patterns of electromagnetic radiation that serve as identifying signatures for intelligence analysis. Military communication equipment, radar systems, and electronic warfare devices each produce characteristic electromagnetic signatures that satellites can detect and catalog. This signature analysis provides intelligence about technological capabilities, equipment inventories, and operational patterns that reveals information about military activities and technological developments. The Naval Ocean Surveillance System demonstrates how satellites track maritime activities by monitoring the electronic emissions from ships and naval vessels. These satellites detect radar transmissions, communication signals, and navigation equipment emissions that allow intelligence analysts to track vessel movements and identify ship types based on their electronic signatures. The system operates by analyzing the electromagnetic patterns produced by different classes of ships, enabling intelligence agencies to monitor naval activities and shipping patterns across global ocean areas. Financial transaction monitoring capabilities focus on intercepting the satellite communications used by banking networks and financial institutions for international money transfers. Intelligence satellites can monitor the communication links used by financial institutions to process transactions between different countries and banking systems. This capability provides information about money flows that support various activities of intelligence interest, but the monitoring focuses on the communication channels rather than direct access to financial networks themselves. Communication network analysis enables satellites to map the electronic infrastructure used by different organizations and nations by monitoring the patterns of electronic emissions and communication activities. Intelligence satellites track how different communication networks operate, identifying the frequencies used, transmission patterns, and network architectures that support various organizations. This network analysis provides intelligence about communication capabilities, organizational structures, and operational patterns that helps intelligence agencies understand how different groups coordinate their activities. Real-time processing capabilities allow satellites to analyze intercepted signals immediately rather than storing raw data for later analysis on the ground. The onboard processing systems can identify communications of immediate intelligence value and generate alerts about significant electronic activities as they occur. This real-time analysis capability eliminates delays that previously limited the operational value of signals intelligence, enabling satellites to provide immediate warnings about electronic activities that indicate developing situations or emerging threats. The electromagnetic spectrum monitoring conducted by intelligence satellites extends across multiple frequency ranges to capture different types of electronic communications and emissions. These systems monitor everything from low-frequency radio transmissions to microwave communications, creating comprehensive pictures of electronic activity in specific geographic regions. The broad spectrum monitoring capabilities enable satellites to detect various types of electronic equipment and communication systems simultaneously, providing intelligence analysts with detailed information about the electronic infrastructure and communication patterns in areas of interest. Modern signals intelligence satellites operate as part of integrated collection networks that combine multiple platforms to provide comprehensive coverage of electronic communications across different orbital positions and frequency ranges. These networks coordinate their collection activities to eliminate gaps in coverage while avoiding interference between different satellite systems. The integrated approach ensures continuous monitoring of priority targets while maximizing the intelligence value extracted from intercepted communications. The sophistication of these electronic monitoring capabilities has created surveillance networks that operate beyond traditional boundaries, establishing new paradigms for intelligence collection and extend far beyond what terrestrial systems can achieve. Yet America's dominance in space-based intelligence faces unprecedented challenges as other nations rapidly develop their own satellite capabilities. The China Challenge, driving innovation through competition. China's rapid satellite development has forced America to accelerate its own space programs in ways that would have been unthinkable just 5 years ago. The U.S. Space Force plans to launch over 100 satellites in 2025, nearly doubling the previously known number of U.S. Space Force spacecraft, a direct response to China's growing space presence. This surge represents the most aggressive satellite deployment timeline in American history, with launch schedules compressed from years to months and development cycles shortened through emergency procurement authorities. The acceleration reflects a fundamental shift in American space strategy from methodical expansion to rapid response, driven by the recognition that China's satellite capabilities are advancing faster than American intelligence agencies previously believed possible. The intelligence arms race that has emerged between the two superpowers in space operates on a scale that dwarfs the Cold War competition between America and the Soviet Union. Both nations are deploying hundreds of new satellites annually while developing capabilities specifically designed to counter each other's surveillance systems. The competition extends beyond simple satellite numbers to include advanced technologies like quantum communications, AI-powered analysis systems, and hardened satellites designed to survive anti-satellite attacks. American intelligence agencies now dedicate significant resources to monitoring Chinese satellite activities while protecting American systems from Chinese surveillance and interference attempts. China's growing constellation threatens American surveillance dominance through a combination of rapid deployment, advanced technology, and strategic positioning that challenges American control over space-based intelligence gathering. Chinese satellites now provide comprehensive coverage of American military facilities, naval movements, and strategic infrastructure through systems that match or exceed American capabilities in many areas. The Chinese constellation includes over 300 active intelligence satellites with capabilities ranging from high-resolution imaging to signals intelligence collection, creating redundant coverage that ensures continuous surveillance of American activities. The Cosmos series of co-orbital inspection satellites demonstrates China's ability to maneuver close to American satellites, conducting detailed examinations of American space assets while potentially positioning themselves for future interference operations. Competition has driven breakthrough innovations in satellite technology and deployment that have accelerated development timelines by decades compared to traditional procurement processes. American satellite manufacturers have adopted rapid prototyping techniques, standardized components, and streamlined testing procedures that reduce development time from years to months. The competition has also spurred innovations in satellite miniaturization, allowing multiple advanced sensors to be packed into smaller platforms that are cheaper to launch and harder to target. Launch capabilities have expanded dramatically, with American companies developing responsive launch systems that can deploy replacement satellites within days of receiving orders. The new doctrine of satellite warfare recognizes the vulnerability of space-based assets and treats satellites as legitimate military targets in future conflicts between major powers. Both American and Chinese military planners now assume that satellite networks will be primary targets in any major conflict, leading to the development of hardened satellites, redundant systems, and rapid replacement capabilities. This doctrine has fundamentally changed how intelligence agencies design and deploy their satellite systems, with emphasis placed on survivability and resilience rather than simply maximizing individual satellite capabilities. The vulnerability of satellites has also led to the development of terrestrial backup systems and alternative intelligence collection methods that can operate when satellite networks are compromised. Both nations are developing anti-satellite capabilities while simultaneously expanding their own networks, creating a paradoxical situation where each country builds systems designed to destroy the same types of systems they are deploying for their own use. American anti-satellite programs include kinetic kill vehicles, directed energy weapons, and cyber warfare capabilities designed to disable or destroy Chinese satellites. Chinese anti-satellite development focuses on similar technologies along with ground-based lasers and jammers that can interfere with American satellite operations. The development of these offensive capabilities forces both nations to design their satellites with defensive features that increase cost and complexity while reducing performance in some areas. The economic espionage battle being fought through competing satellite systems extends beyond traditional military intelligence to include monitoring of industrial activities, trade flows, and technological development programs. Chinese satellites monitor American manufacturing facilities, ports, and research installations to gather intelligence about American economic activities and technological capabilities. American satellites track Chinese military-industrial facilities and analyze Chinese economic activities to understand Chinese strategic intentions. Both nations use satellite intelligence to support their domestic industries through advance warning about competitor activities and market developments. technological leapfrogging has accelerated development timelines for both nations as each country attempts to deploy advanced capabilities before their competitor can develop countermeasures. American satellite programs now incorporate technologies that were experimental just years ago, while Chinese programs demonstrate capabilities that American intelligence agencies did not expect China to achieve for another decade. The competition has compressed normal technology development cycles as both nations prioritize rapid deployment over thorough testing and gradual improvement. The competitive dynamic has also driven both nations to pursue revolutionary rather than evolutionary improvements in satellite technology, leading to breakthrough capabilities that represent fundamental advances rather than incremental improvements. Quantum processing, artificial intelligence, and advanced materials technologies that were laboratory curiosities have been rapidly deployed to space systems because of competitive pressure to maintain technological advantages. The competition has essentially forced both nations to deploy their most advanced technologies to space applications years ahead of normal development schedules. This satellite arms race has created an environment where both nations continuously expand their surveillance capabilities while developing countermeasures against each other's systems. The result is an accelerating cycle of technological advancement that pushes the boundaries of what space-based intelligence can achieve. Yet this competition has also created new vulnerabilities and dependencies that recent conflicts have exposed. The Russian factor. Lessons from Ukraine. The Ukraine conflict revealed how satellite intelligence has evolved from supporting military operations to determining their outcomes entirely. Ukrainian forces received real-time intelligence about Russian troop movements, equipment positioning, and operational plans through American satellite systems that provided information faster and more accurately than traditional military reconnaissance methods. This intelligence enabled Ukrainian commanders to anticipate Russian attacks, position defensive forces effectively, and coordinate counteroffensives with precision that would have been impossible using ground-based intelligence gathering alone. The conflict marked the first time in military history that satellite intelligence directly influenced tactical decisions on an hour-by-hour basis rather than providing strategic background information for long-term planning. American satellites provided battlefield intelligence that changed the course of the war by enabling Ukrainian forces to track Russian military movements as they occurred rather than discovering them after the fact. Satellites monitored Russian supply convoys as they moved toward the front lines, providing Ukrainian forces with advance warning that allowed them to position anti-tank teams and artillery units to intercept these convoys before they could deliver supplies to Russian combat units. The real-time nature of this intelligence eliminated the traditional fog of war that had historically protected military movements from enemy observation. Russian commanders found that their operational plans were being countered almost immediately after implementation because Ukrainian forces received satellite intelligence about Russian activities within minutes of their initiation. The continuous struggle between Russian forces and American surveillance satellites demonstrated the extent to which modern military operations depend on space-based intelligence systems. Russian electronic warfare units deployed jamming equipment designed to disrupt satellite communications and blind American surveillance systems, but these efforts achieved limited success against satellites equipped with advanced signal processing and adaptive communication systems. Despite Russian attempts to jam and disable these satellites, the United States maintained its surveillance capabilities, providing crucial intelligence to Ukrainian forces throughout the conflict. Russian forces attempted to camouflage their activities using traditional military deception techniques like camouflage netting and decoy equipment, but satellite sensors operating across multiple electromagnetic spectrums could detect concealed equipment through thermal signatures, synthetic aperture radar, and spectral analysis that penetrated most concealment efforts. Satellites enabled precision strikes and exposed Russian military movements through integration with Ukrainian weapon systems that could receive targeting data directly from orbital platforms. American satellites identified high-value Russian targets like command centers, ammunition depots, and electronic warfare systems, then transmitted targeting coordinates to Ukrainian forces within minutes of target identification. The precision of satellite-guided strikes forced Russian forces to disperse their assets and avoid concentrating equipment in ways that had been standard military practice for decades. Russian military movements that would have been invisible to traditional reconnaissance became clearly visible to satellite systems that tracked individual vehicles and personnel across vast areas of terrain simultaneously. The conflict served as a testing ground for new satellite-based warfare capabilities that had been theoretical concepts before being deployed in actual combat conditions. Artificial intelligence systems aboard American satellites automatically identified Russian military equipment and flagged high-priority targets without human intervention, demonstrating that automated warfare systems could operate effectively in real combat environments. Satellite mesh networking capabilities allowed intelligence information to flow between orbital platforms and ground forces without passing through traditional command structures, creating direct battlefield communication links that bypassed potential points of failure or interception. These new capabilities proved their effectiveness under combat conditions that provided the ultimate test of their operational value. Satellite intelligence made traditional military deception nearly impossible because orbital surveillance systems can detect military activities through multiple sensor types that operate independently of weather conditions, lighting, and concealment efforts. Russian forces discovered that camouflage techniques effective against ground-based observation provided little protection against satellite sensors that could detect equipment through thermal signatures, radar reflections, and electromagnetic emissions. Military deception operations that relied on hiding equipment or creating false targets became ineffective when satellite systems could distinguish between real and fake equipment through spectral analysis and behavioral pattern recognition. The comprehensive nature of satellite surveillance eliminated the operational security that military forces had historically relied upon to protect their activities from enemy observation. The conflict accelerated the development of next-generation military satellites by proving the operational value of space-based intelligence and identifying specific capability requirements that emerged from actual combat experience. American satellite programs inked lessons learned from the Ukraine conflict by developing enhanced electronic warfare resistance, improved target recognition algorithms, and faster data transmission systems that could provide intelligence to ground forces more quickly. The conflict demonstrated that satellite intelligence systems needed to operate autonomously for extended periods without ground-based control, leading to the development of artificial intelligence systems that could make targeting decisions independently. Commercial satellites became legitimate military targets for the first time when Russian forces recognized that commercially operated satellites were providing military intelligence to Ukrainian forces through data-sharing agreements with American intelligence agencies. Russian military planners began treating commercial satellite operators as combatants rather than neutral parties because their satellites were directly supporting Ukrainian military operations. This targeting of commercial satellites represented a fundamental change in military doctrine that extended the battlefield into commercial space operations that had previously been considered civilian infrastructure protected from military targeting. The Ukraine conflict established that military forces without effective satellite intelligence operate at decisive disadvantages that traditional military capabilities cannot overcome. Modern warfare now requires satellite intelligence for basic military operations, making space-based systems essential rather than supplementary military assets. Yet the same surveillance technologies that proved decisive in military conflicts have found applications far beyond warfare, extending their reach into domains that affect global commerce and international relations in ways that most nations are only beginning to understand. Beyond Earth, climate and economic surveillance. Satellite surveillance has expanded far beyond military applications into comprehensive monitoring of global economic activity and environmental changes. These orbital platforms now track shipping patterns, agricultural conditions, and industrial activities that serve as leading indicators for broader economic trends. Commercial imagery providers like BlackSky deliver 1-meter resolution imagery used for monitoring disaster recovery and crop yield forecasts, transforming how governments and businesses understand economic conditions worldwide. The economic intelligence gathered through satellite observation provides information that was previously impossible to obtain through traditional monitoring methods. Port traffic analysis reveals changes in trade volumes weeks before official trade statistics become available, allowing economists to forecast economic growth or contraction based on shipping activity patterns. Satellites monitor major shipping routes and port facilities to identify increases or decreases in cargo movement that indicate changing trade flows. Agricultural monitoring identifies crop stress, irrigation changes, and planting patterns that predict food prices and commodity market fluctuations months in advance. Commercial satellite systems track vegetation health and soil moisture levels across major agricultural regions, providing early warning about potential harvest shortfalls or surplus production that will affect global food markets. Industrial activity tracking includes monitoring of factory emissions, energy consumption patterns, and transportation networks that indicate manufacturing output levels before companies release quarterly earnings reports. Satellites can detect changes in industrial activity through thermal signatures from manufacturing facilities, emissions patterns from power plants, and transportation activity around major industrial centers. This industrial monitoring provides intelligence about economic conditions that may not be reflected in official economic statistics or corporate reporting until months later. Environmental monitoring has become a tool for economic and political intelligence because climate conditions directly affect resource availability, agricultural production, and population stability in ways that influence international relations. Economic policy. Drought monitoring in major agricultural regions provides advance warning about food security issues that can trigger political instability or migration patterns that affect neighboring countries. Water resource monitoring reveals potential conflicts over scarce water supplies that could lead to international disputes or internal political tensions. Climate change impacts on coastal areas provide intelligence about future infrastructure needs and population displacement that will affect economic development and political stability. Satellites track energy infrastructure and can predict political instability through monitoring of power generation facilities, transmission networks, and energy consumption, patterns that reveal economic stress and social tensions. Power grid monitoring identifies areas experiencing electricity shortages that often precede social unrest or political protests. Energy infrastructure attacks or sabotage can be detected immediately through satellite monitoring of power plants, pipelines, and transmission lines. Changes in energy consumption patterns reveal economic problems or social tensions that may not be apparent through other intelligence sources. Agricultural monitoring affects global food security and commodity markets through detailed analysis of crop conditions, planting decisions, and harvest yields that determine food prices and availability worldwide. Satellites monitor soil moisture levels, vegetation health, and weather conditions that affect crop yields months before harvest, enabling accurate predictions of agricultural production that influence commodity trading and food policy decisions. Detailed crop monitoring reveals which countries will have surplus production and which will face shortages, affecting international trade patterns and food assistance requirements. Agricultural intelligence also identifies emerging plant diseases or pest infestations that could spread to other regions and affect global food production. Climate change monitoring provides strategic intelligence about resource availability and migration patterns that affect national security planning and economic development strategies. Satellite data reveals how changing precipitation patterns affect agricultural productivity in different regions, providing intelligence about future food security issues that could trigger migration or political instability. Monitoring of glacial retreat and sea level rise provides information about future water availability and coastal infrastructure vulnerability that influences long-term economic planning and national security assessments. Temperature and weather pattern analysis helps predict climate-related migration patterns that will affect regional stability and economic development. This economic intelligence influences American foreign policy and trade negotiations by providing detailed information about economic conditions, resource availability, and trade patterns in countries around the world. Satellite intelligence about agricultural production affects food assistance programs and agricultural trade policies. Economic activity monitoring influences trade agreement negotiations by revealing actual economic conditions rather than relying on official statistics that may be inaccurate or manipulated. Resource availability intelligence affects energy policy and strategic resource acquisition programs. Economic warfare is now fought primarily through satellite intelligence because comprehensive economic monitoring provides the information necessary to implement targeted economic pressure campaigns and evaluate their effectiveness. Satellite intelligence enables precision economic targeting that can disrupt specific industries or resource flows while avoiding broader economic impacts. Economic pressure campaigns can be calibrated based on real-time satellite intelligence about their effectiveness, allowing policymakers to adjust economic measures to achieve specific political objectives. The comprehensive nature of satellite economic monitoring means that these systems have become essential infrastructure for modern economic policy and international relations. Yet the same satellites that provide this economic intelligence have also become valuable targets themselves, creating new vulnerabilities that extend far beyond traditional military considerations. The space militarization dilemma. Military planners across the globe now recognize that space itself has become the next battlefield, fundamentally altering how nations prepare for and conduct warfare. The growing militarization of the orbital environment represents one of the most significant shifts in military doctrine since the development of nuclear weapons. Nations are developing capabilities specifically designed to target and destroy satellites that were once considered safe from direct military attack, the peaceful domain of space that hosted scientific missions and communication. Satellites has transformed into a potential theater where future conflicts between world powers will likely begin. Surveillance satellites have become primary targets in potential future conflicts because they represent the eyes and ears that enable modern military operations. Russian and Chinese military strategists recognize that American military superiority depends heavily on satellite intelligence and communication systems that coordinate everything from precision strikes to logistics operations. Destroying or disabling these satellites would blind American forces and eliminate many of the technological advantages that American military doctrine assumes will be available during conflicts. The targeting of surveillance satellites represents a fundamental shift from viewing space assets as civilian infrastructure to treating them as legitimate military targets that determine the outcome of terrestrial conflicts. The development of anti-satellite weapons by multiple nations has accelerated dramatically as space becomes recognized as a critical military domain. Russia's Cosmos series satellites, including Cosmos 2543 and Cosmos 2576, have been conducting what appear to be anti-satellite training missions, practicing attack and defend tactics in low Earth orbit. China demonstrated advanced co-orbital satellite maneuvers in December 2024 that position attacking satellites close to target satellites. These developments show that both kinetic weapons that destroy targets through physical impact and non-kinetic methods using electronic warfare or cyber attacks are being actively developed and tested. The U.S. Space Force is preparing for potential space conflicts by developing both offensive and defensive capabilities designed to achieve what General Chance Saltzman calls space superiority. The Space Force is testing new satellite jammers called remote modular terminals that operate remotely and provide counter-space electronic warfare capabilities against enemy satellite communications and control systems. These systems represent a shift toward non-kinetic anti-satellite weapons that can disable enemy satellites without creating the debris field that kinetic weapons produce. The remote modular terminals can jam satellite communications and potentially disrupt enemy satellite operations while maintaining plausible deniability about the source of the interference. Satellite constellations are being designed to survive coordinated attacks through redundancy, hardening, and rapid replacement capabilities that ensure critical intelligence and communication functions continue operating even when individual satellites are destroyed or disabled. Modern satellite networks include hundreds of platforms distributed across multiple orbital planes so that losing any single satellite or even multiple satellites has minimal impact on overall system performance. Satellites now incorporate shielding and electronic countermeasures designed to resist attacks from anti-satellite weapons. Rapid replacement programs maintain inventories of ready-to-launch satellites that can restore constellation capabilities within days of any losses sustained during conflicts. The Kessler Syndrome threat limits aggressive actions against satellite networks because destroying satellites creates debris fields that threaten all spacecraft operating in affected orbital regions. Named after NASA scientist Donald Kessler, This syndrome describes a cascade effect where destroyed satellites create debris that destroys other satellites, which create more debris that destroys even more satellites until entire orbital regions become unusable. The threat of triggering Kessler syndrome provides a natural deterrent against kinetic anti-satellite attacks because nations recognize that destroying enemy satellites could make space unusable for their own satellites as well. Cyber warfare against satellites represents a new domain of conflict that operates outside traditional concepts of military engagement and territorial boundaries. Satellite systems depend on complex software and communication networks that are vulnerable to cyber attacks that can disable or manipulate satellite functions without physical destruction. These cyber attacks can be conducted remotely without revealing the identity of the attacking nation, creating attribution challenges that complicate military responses. The increasing reliance on commercial satellite systems creates additional vulnerabilities because commercial operators typically have less robust cybersecurity than military systems. The Secure World Foundation's report on counterspace capabilities highlights the challenge of establishing international norms for space warfare when multiple nations are developing offensive capabilities simultaneously. Current international space law was developed for peaceful space exploration rather than military conflict, leaving critical questions unanswered about the legal status of satellite attacks and appropriate responses to space-based aggression. The lack of clear legal frameworks means that nations must make decisions about space warfare without established precedents or international agreements that define acceptable behavior. The paradox that emerges from space militarization is that the tools meant to prevent war may trigger conflicts by creating new vulnerabilities and attack vectors. Anti-satellite weapons developed for deterrence create capabilities that adversaries may choose to use preemptively rather than risk losing their own satellites to similar attacks. Commercial operators find themselves caught in the crossfire of geopolitical tensions as their satellites become legitimate military targets. The competition to control or deny access to space intensifies as nations recognize that space superiority determines terrestrial military outcomes. This militarization of space occurs alongside technological advances that promise to make satellite surveillance more comprehensive and pervasive than ever before, raising questions about the future of omniscient surveillance. The technological trajectory of these developments have established points towards surveillance capabilities that intelligence officials describe as constant stare, the ability to maintain continuous observation of any target on Earth without interruption. Current satellite systems provide periodic coverage that captures snapshots of activities at specific times, but constant stare systems would monitor targets continuously, day and night, week after week, year after year. This capability requires satellite constellations dense enough to maintain multiple platforms over every location on Earth at all times, creating surveillance networks that never lose sight of their targets. The decreasing cost of satellite technology makes this level of coverage financially feasible for the first time in history. The National Reconnaissance Office has outlined the most ambitious expansion in satellite surveillance history through Director Christopher Scali's plan to quadruple the number of NRO satellites in space and increase the volume of imagery and data they provide to sister agencies tenfold within a decade. This expansion represents the foundation for surveillance capabilities that approach comprehensive global monitoring through sheer volume and coverage density. The plan moves beyond current capabilities towards systems that can track activities across the planet simultaneously through overlapping satellite coverage that eliminates the gaps and delays that currently limit intelligence gathering operations. Major General Stephen Purdy has confirmed that the United States is reevaluating its reliance on costly singular satellite systems in favor of a proliferated satellite architecture that enhances resilience and cost efficiency. This shift toward distributed satellite networks creates redundant coverage that ensures surveillance capabilities continue operating even when individual satellites are destroyed or disabled. The proliferated approach deploys dozens of smaller satellites instead of relying on a few expensive platforms, making the overall system nearly impossible to disable through attacks on individual satellites while dramatically reducing the cost per satellite and shortening deployment timelines. The technical challenge of managing the massive increase in data volume from quadrupled satellite constellations requires fundamental changes in how intelligence agencies process and analyze information. Current data processing systems struggle to handle the information streams from existing satellite networks, and a tenfold increase in data volume will require completely new approaches to information management and analysis. The Space Force will need significant expansion to manage the influx of data from hundreds of additional satellites, with new facilities, personnel, and processing systems dedicated to handling the unprecedented volume of intelligence information these expanded constellations will generate. Commercial satellite integration has become essential to achieving constant stare capabilities through partnerships that leverage civilian-operated satellites alongside government systems. The NRO has diversified its sources and methods of observation over the past 2 years, incorporating electro-optical imagery, radar imagery, radio frequency data, and hyperspectral information from commercial providers. This diversification challenges the efforts of nations that attempt to conceal their most threatening attack and defense projects by creating multiple independent sources of surveillance information that are difficult to counter simultaneously. The proliferated architecture approach creates surveillance networks that can maintain continuous coverage through coordinated satellite operations that ensure multiple platforms observe the same targets from different orbital positions. This overlapping coverage eliminates the surveillance gaps that exist when fewer satellites are available and targets can only be observed during specific orbital passes. Multiple satellite views of the same location also enable detailed analysis that creates comprehensive pictures of activities and changes over time rather than isolated snapshots of specific moments. Advanced artificial intelligence systems will become essential for processing the massive data streams from expanded satellite constellations, analyzing patterns across multiple sensors simultaneously to identify activities and anomalies that human analysts could never detect manually. These AI algorithms can process vast datasets from multiple sensors, enabling early detection of activities and proactive responses to developing situations before they reach critical stages. The integration of AI with satellite surveillance creates automated analysis capabilities that can monitor global activities continuously without requiring human oversight for routine operations. The constant stare capability will reshape international relations by making surprise attacks and covert movements of large weapons or equipment nearly impossible to conceal from satellite observation. Military buildups that previously could be hidden through camouflage and operational security will become visible to surveillance systems that monitor the same locations continuously over extended periods. The ability to track changes in military activities, infrastructure development, and resource movements in real time will provide intelligence agencies with unprecedented insight into the intentions and capabilities of foreign nations. This surveillance expansion occurs alongside growing recognition that space itself has become a contested domain, where nations compete for information dominance through satellite capabilities that determine terrestrial power relationships. The nation that achieves comprehensive satellite surveillance first will possess decisive advantages in diplomatic negotiations, military planning, and economic competition because they will understand the activities and intentions of other nations with unprecedented clarity. The race to deploy constant stare capabilities represents competition for a form of information superiority that could fundamentally alter how power operates in international relations. The implications of achieving truly comprehensive satellite surveillance extend beyond traditional intelligence gathering into questions about the nature of power itself in an age of orbital omniscience. America's 2025 satellite constellation represents a fundamental shift from episodic Cold War-style reconnaissance to near-constant multi-orbital coverage that operates around the clock. The expansion from Corona's film return missions to today's proliferated architecture creates surveillance capabilities that previous generations of intelligence planners could never have imagined. Low Earth orbit constellations. Commercial partnerships with companies like Planet Labs and Maxar and AI-driven analysis systems have transformed space-based intelligence from periodic observation into continuous monitoring that shapes international relations and military planning. The strategic importance of these capabilities extends beyond traditional intelligence gathering into questions about how nations will responsibly apply these space innovations. The development of international norms around debris, creating anti-satellite tests and cyber frameworks for space operations becomes essential as more nations deploy advanced satellite systems. The technology that emerged from competition between superpowers now requires cooperation to ensure space remains accessible for peaceful purposes while serving legitimate national security